This video will bring you through some sections of the SEM. First, a little bit about the components of SEM, followed by the concepts and theory, and lastly, the procedure on SEM. The purpose of scanning electron microscopy is to attain high-resolution 3D imaging by scanning the surface of a sample using a focused beam of electrons. Hence, SEM is a surface-based technology. Before explaining how the SEM works, we need to understand the main parts of an SEM and their general function. First is the electron gun located right at the top of the SEM machine. There are different types of electron guns such as field emission gun and thermonic gun, but they all serve the purpose of generating an electron beam. The second part are the series of lenses, which correct the path of the electron beam and direct it to the specimen. Most of the time, the motion of the electron beam is controlled by magnetic field generated by a coil of electric wires. Sample chamber is where the specimen is added and stored during analysis. Detector. Depending on the type of electrons measured, there are varying types of detectors. Most SEMs are equipped with a secondary electron detector, backscatter detector, X-ray detector for the EDS sample. However, secondary electron is the most common mode used. So how does an SEM work? Conceptually, the electrons that are bombarded onto the sample interact with the sample in various ways, and thus produce signals which is read by the detector. This information provides topographical image of the sample. To generate an image, the incident electron beam is raster scanned across the surface, depending on the interaction of the electron to the atom and whether it is an elastic or inelastic interaction. The image can be generated in secondary electron mode or backscattered electron mode. Most of the time, secondary emission is used to attain the image. A plus point of SEM is that it allows for elemental analysis via the EDS mode, which electron bombardment brings about characteristic X-rays of the element and thus giving elemental composition. Things to take note. SEM requires the sample to be conductive, and thus silicon wafers are used and a drop cast method is adopted to attain nickel nanoparticles and gold nanocubes in this experiment. Non-conducting samples need to be sputtered with gold to obtain conductivity. In addition, SEM is conducted in a vacuum chamber, and thus the sample has to be compatible with vacuum. Hence, living biological samples can't be analyzed via SEM. Depending on the type of sample you have, you need to prepare it accordingly. In this case, a drop cast has been done on silicon wafers and left to dry. It is then attached to a holder via carbon tape and then placed onto a sample holder and secured. The specimen is mounted onto the specimen holder and the specimen height is adjusted to be the same level as the specimen. Mount the holder with the specimen on the specimen exchange stage with the double-headed arrow pointing parallel with the clamp and then lock the airlock.
Then press down, lock. So when you lock, you have to pump down all the...
Pump the airlock by pressing the evac button, which will be flashing during the pumping. The evac sequence is complete when the button stops flashing. Then, load the sample holder on the stage by pushing straight forward the exchange rod with the holder on the stage. The holder indicated should be lighted. Precaution should be taken when handling the rod. The rod should be gently tilted into a horizontal position and slide it slowly. Never rotate or tilt the rod. Press the vent button to vent the airlock. This ensures the safety of the vacuum system. Once the sample is in, a small window will pop out, which indicates the vacuum in the chamber. Wait till the vacuum in the chamber is 9.63 to the power minus 5, or at least 1.91 to the power minus 4 pascals. Check the color of the HT button. It will change from black to blue, indicating that it can be turned on, and green when in operation. This will turn on the gun emission. Wait till the emission current reaches 10 microampere. To get the imaging, adjust the stigmators X and Y and the contrast. To collect the image, select the Find View button, which gives a slow scan speed, and press Freeze to keep the image in memory. To save the file, click Image File Handler and export the image.
The gauge is
When unloading the sample, switch to LEI and hit the HT off button, and the button will change color to blue. Recall the stage exchange position to x equals to 35, y equals to 25, r equals to 0, z equals to 8, and the tilt equal to 0. On clicking exchange or home, the SEM will automatically reset the coordinates. Press evac and wait till the sample stops flashing. Once it stops flashing, remove the sample using the rod slowly. Remove the sample and press vent. Once it stops blinking, open the airlock and pull the sample out. Close the airlock and press evac
then
again.
you have to evac again.
Using this picture, the base to peak length of the object can be deduced from the scale shown at the bottom. In this case, 1 micrometer is equal to 0.6 cm, and the length is 4.8 cm. Therefore, the image has a length of 8 micrometer. It is also worthy to note that the magnification in the image is inaccurate, as 8 micrometers multiplied by 10,000 equals to 8 cm. However, the image in the screen has been shrunk and hence inaccurate. From the image, we can see that 5 keV is the energy of the electron. Therefore, by multiplying the mass of the electron, you can get the square of the momentum. From the momentum, we can calculate the wavelength by adopting the de Broglie equation, which has a value of approximately 10 to the power minus 11. Resolution depends on lambda, and therefore having a lower lambda leads to a better resolution. A typical SEM image has a resolution of approximately 1 nanometer, and that is its maximum. This is higher than the de Broglie wavelength calculated, which is 2 orders magnitude lower. This difference in the lambda can be explained via the Heisenberg uncertainty principle, which states that the position and the momentum of an electron cannot be accurately determined at the same time. Since SEM uses the position and the momentum at the same time for imaging, and therefore the uncertainty is larger and hence compromises the resolution. Thanks for watching. That's all we have. Let's end with an interesting SEM image from Mars.